Well, good afternoon. This is 12:51 on Tuesday, November 8th, Election Day. As I told you, I had a doctor's appointment this morning at 8, so we couldn't meet class then, and several of you said you could meet at 12:30 today, and I have waited about as long as I can. Actually, there was an extra delay in the fact that my computer wouldn't boot off. It booted off 2 or 3 times this morning when I was waiting at UAB at the Kirkland Clinic and it did fine, but when I got here to class for my 11 o'clock class, it would not boot off. So I had to take it down. The IT person had to completely unload everything, redo something, and load it back up. So it is working now, but sorry about the lateness getting started. I'll try to do about an hour and 15 minutes of class, counting what we're doing now, and stop it then. So we'll go past 1:45, which is what did I say we would be going. But no students are in the room. I'm here by myself, so I'll just do as much as I can and explain this, and it'll be on Screencast-O-Matic, hopefully sometime this afternoon or evening. I don't know when I'll be able to get it into the right playlist, because I've got class at 3:15 today. I don't know if it'll be fully loaded by then. Let me just go over a couple things. This has been a strange week because of my doctor's appointment and other things. Office hours today start as soon as this class is over with, but only go to 3:15 because that's when my next class starts, and that goes until 7:45. So there won't be many more office hours today, just from whenever this ends till 3:15. Tomorrow, Wednesday, is a fairly normal day. My office hours are only 11:15 to 12:15. That's also when I eat, but I can handle people in the office then. But then, also, I'm usually available shortly after, at 2 o'clock. I usually don't leave at 2, even though that's what time I'm supposed to leave. I will be there for a while after 2 o'clock. Okay. Then Thursday, it would be a normal day, except that we have a faculty meeting at 2:30. So normally my office hours would be 12:15 to 3:15, but on Thursday they'll only be 12:15 till 2:15 because I'll leave to go to the faculty meeting shortly after 2:15 to be there by 2:30. And then Friday is not normal either because it's Veterans Day. There's no school that day. College is closed, so I will not have any office hours, of course, on Friday. Next week should go back to normal. Mondays and Wednesdays, 11:15 to 12:15, and sometime after 2. And then Tuesdays and Thursday, 12:15 to 3:15, and then Friday from 7:45 to 11:45 on the Birmingham campus. All right, that's all I can think of there. Let's go on and get started. I believe that we finished 2.4. That was just a slideshow on 2.4. I won't go any further there. So we're starting today in 2.5. Chapter 2, again, is polynomial and rational functions. We have been doing polynomial functions, and we'll continue doing that through 2.5, but then 2.6 will be the rational functions. So this is the last section on polynomial functions, 2.5. And this is talking about the zeros of polynomial functions. Now, we've already been dealing with zeros, so this is nothing new, but we're going to have a few new techniques, a few new theorems, ways to go about finding. So put a few more tools on our tool belt that help us find these zeros. Okay? So first we'll talk about the fundamental theorem of algebra. It says to determine the number of zeros of polynomial functions. Now we've already had just the edge of this, okay, when we said we could have up to n zeros for an nth degree polynomial, but you didn't have to have them. Now we'll talk about them to the full fundamental theorem of algebra. Secondly, we'll find rational zeros of polynomial functions. That's going to be the biggest, most useful tools we have. We'll talk about conjugate pairs of complex zeros. We're not going to go into that in any depth or detail because you're not responsible for that by the course description, but I will show it to you. And we'll find zeros of polynomials by factoring, which is what we've done in the past, but we'll use rational zeros and other things to improve our factoring capabilities. We'll use Descartes' rule of signs and the upper and lower bounds to find zeros of polynomial functions. They're just additional tools to give us a few additional hints and clues. They won't find them for us, but they give us information. And then we'll find zeros of polynomials in some real-life applications. All right, let's start with the fundamental theorem of algebra. Now, remember section 2.4 that we just sort of did a slideshow on? That introduced complex numbers. We had been dealing only with real numbers before then. Now we're dealing with complex numbers. In the complex numbers system, get this, every nth degree polynomial function has precisely n zeros. Okay? Now if you think back when we're dealing with real numbers, we said in the real number system, an nth degree polynomial has up to n real zeros. May have fewer, but it can't have any more than n. In the complex number system, we know it has exactly n zeros. Now, the difference between the number of real zeros and the number of complex, the n, that's going to be all complex zeros in between there. And we're not going to mess with those. We'll introduce them to you, but that's all. This important result is derived from the fundamental theorem of algebra that was first proved by the German mathematician Carl Friedrich Gauss. Boy, you talk about a mathematician who was prolific. Gauss was, okay? He lived 1777 to 1855. To put that in terms of, that was over in Germany. Here in the U.S., we were not yet, we had declared our independence in 1775, so this is 2 years after that he was born. We hadn't really formed the country yet until later. We were under Articles of Confederation for a while, and then ultimately under the Constitution that was around 1780, 81, 80, something in there. Okay, so that's when he was born. Okay, he died just before our war between the states happened, 1855. So he lived, that's 55 plus 23, 78 years. So pretty long life back at that time. Very prolific mathematician. And he first proved this, and I think your book will also mention another guy who worked on it independently from him. But here's what the fundamental theorem of algebra says. And by the way, Gauss is a potential paper topic. Fundamental theorem of algebra is a potential paper topic. How did Gauss develop this was a potential paper topic. Other mathematical things Gauss did, those are potential paper topics. Got a whole trove of possibilities here with him. Get your papers in. Hint, hint. Okay, the fundamental theorem of algebra. If f of x is a polynomial of degree n, as long as n is greater than 0, not much of a degree if it's equals 0, okay, then f has at least 1 0 in the complex number system. Okay, boy, that's pretty straightforward. At least 1 0. We just said above here it's going to have precisely n zeros. Every nth degree polynomial will. Well, the fundamental theorem of algebra starts with the simple, at least 1 0 in the complex number system. Now, does that mean they're all complex zeros? Not, yeah, it does, but the thing is, remember, all real numbers are complex numbers. Not all complex numbers are real numbers. So these could be real zeros. They could be integer zeros. They could be rational zeros. They could be complex zeros, okay, imaginary zeros. But it has at least 1 0 in the complex number system. Sounds like a pretty simple theorem, but Gauss was the first one to actually prove it. Sometimes these simple ones are the hardest to prove. So using the fundamental theorem of algebra and the equivalence of zeros and factors, remember what that is? If x equal a is a solution or a zero of a function, then x minus a is a factor of that polynomial expression. Okay? So here we get the linear factorization theorem. If f of x is a polynomial of degree n, where n is greater than 0, of course, then f of x has precisely n linear factors. And these linear factors could be expressed this way. F of x is equal to a sub n, that's some coefficient of the nth term, a sub n, times x minus c1 times x minus c2 times x minus c3 times x minus c4 up to and including x minus cn. Now those c1s through cn's are complex numbers. They could be real, they could be rational, they could be integral, but they definitely are complex. Okay? This says a polynomial of degree n will have precisely n linear factors. If it has n linear factors, then we can set that equal to 0 and say x equals c1, x equals c2, x equals c3. Those could be our zeros. Complex zeros, or real, or rational, whatever. Okay? Note that the fundamental theorem of algebra and the linear factorization theorem tell you that the zeros or factors of a polynomial exist. It just doesn't tell you how to find them. Such theorems are called existence theorems. Okay? Here is example 1. This is on page 154 in section 2.5, chapter 2 of your text. The first degree polynomial, f of x equal x minus 2, has exactly 1 0. Happens to be a real 0. Happens to be an integral 0. Happens to be a rational 0. And of course it's a complex 0 as well, because all those are complex numbers as well. We know that because when you set this equal to 0, let me get my pen back to black, set that equal to 0, solve for x, add 2 to both sides, and you get x equal 2. Okay? So f of x equal x minus 2. Obviously, that's a factor of the function. In fact, it's the only one. 1 times x minus 2 is x minus 2. And because it's a factor, x equal 2 is a 0, and that's it. It's a first degree polynomial. It only has 1. Don't look for any more. That's it. Done. Okay? That was awfully simple, wasn't it? Okay? Now, the B part, counting multiplicity, the second degree polynomial function, f of x equal x squared minus 6x plus 9, how many zeros does that have? Well, what we would do, we'd set it equal to 0. We'd see if we can factor it. And if you are really on the ball, you might note that is a perfect square trinomial. But if you don't see that, you could try x times x, minus times minus, 3 times 3, and sure enough, that works. X times x is x squared, minus 3x is minus 6x plus 9. That's it. Therefore, these two are factors. That means x equal 3 is a solution or a 0 of that polynomial. But because that's a factor twice, we could write that x minus 3 squared is equal to 0. We say it has a multiplicity of 2. So counting multiplicity, that second degree polynomial function also has 2 real roots, integral roots, rational roots, and of course complex roots. Okay? But they just happen to be the same number because of the multiplicity. Okay? I'm going to clear the slide because I need to write something else on here. And here's this, oops, they do the same thing we did. They factored it, x minus 3 times x minus 3. Has exactly 2 zeros, even though they're the same number, x equal 3 and my brother x equal 3. Same value. It's called a repeated 0 or a 0 of multiplicity 2. Okay? So it does have 2. A second degree polynomial will always have exactly 2 complex roots. These both happen to be the same number, but they're real. Okay, here's a third degree polynomial function. Okay? If you set that equal to 0, factored this, that would be x times x squared plus 4 equals 0. Well, I see one. X equals 0 is a real, complex, rational integral root. Okay, that's x equals 0. However, if you try to do x squared plus 4 equals 0, you see you can't do that in the real number system. And don't worry about it because you're not responsible for it, but just giving you the answer because we're going to do it in a minute. That would be x equal plus or minus 2i. Two more complex roots or zeros, okay? Because if you square 2i, you get 2 times 2 is 4. I times I is I squared, which is negative 1. That would be negative 4 plus 4 is 0. If you did minus 2i, minus 2 times minus 2 is still plus 4. I squared is still minus 1, so that would be minus 4 plus 4 is 0. So those are your two complex roots for that one. You're not responsible for that. We're only going to be dealing with the real roots. But I'll clear this out of the way just so you can see how they did it as well. Oops. I went to clear it and didn't clear. There we go. Same thing we did. Factor all you can. That gives you either x times x minus 2i times x plus 2i. Exactly 3 zeros. X equals 0 the first one. X equals 2i the second. X equals minus 2i the third. Only one of those is real. The other two are complex. They're all complex. They have some imaginary parts. All right. That was example 1. Now we're moving to the rational zero test. And by the way, there is a checkpoint there. Try working that one too. I'll look at that and tell you it will have 2 real roots and 2 complex roots. You don't have to worry with the complex, but it'll only have 2. All right, let's look at 155. Page 155. The rational zeros test. This gives us a tool to help us find some of the zeros. It won't find complex zeros for us, though it might eliminate some others so you get you down where you can find the complex zeros. It won't give you irrational zeros, though it will maybe get you to the point where you can find them by another means. So finding zeros of polynomial functions is a very important concept in algebra. It's a good place to discuss the fact that polynomials do not necessarily have rational zeros, but may have zeros that are irrational or complex. But again, the rational zero test is a good tool. Okay? Here's what it is. Rational zero test relates the possible rational zeros of a polynomial. Now, those polynomials we're talking about are those having integer coefficients. Okay? Most of the ones we've dealt with have had integral coefficients. However, if you had any that had 0.5 x squared minus 0.327 x plus 0.57, you won't be able to use rational zeros test for that. But how many of those have we seen? Basically, very few, if any. Okay? If you have integral coefficients, no fractions, no decimals, all integral coefficients, then the rational zeros test relates the possible rational zeros of the polynomial to 2 entities. First, the leading coefficient, that's been important for us before, but also the constant term at the end. So the bookends. So if a polynomial function f of x is a sub n times x to the n plus a sub n minus 1 to x to the n minus 1 plus, keep on counting down with your powers of x till you get to a2 x squared plus a1 x to the first plus a0 times x to the 0, which is 1. If all those a's are integers, okay, plus or minus, it doesn't matter, no fractions, no decimals, then every rational zeros, not all the zeros, but all the rational zeros of that function f has to be of the form p over q. Well, I mean, a rational zero would have to be of that form. P is some integral number, Q is some integral number. But what are these? Where P and Q have no common factors other than 1, so you couldn't have a 8 over 6. That wouldn't work. You have to get it to no common factors. 4 over 3, that would work because it doesn't have any common factors other than 1. But where does this P come from? A factor of your constant term A0. That last term down here, that's where the P comes from, the A0. Where does the Q come from? It is a factor of your leading coefficient, A sub n. Okay? That's the rational zero test. Any rational zero is going to be of the form of some factor of that constant term in your numerator and a factor of your leading term in the denominator. So, to use the rational zero test, you should first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. So the possible rational zeros are all the factors of the constant term divided by all the factors of the leading coefficient. Once you form that list of all the possible rational zeros, then use trial and error method to determine which, if any, are actual zeros of the polynomial. Remember, this is just a tool. It's not going to tell you what they are, but it eliminates ones that are not. Note that when the leading coefficient is 1, that's really nice because the possible rational zeros are simply the factors of that constant term. Okay? So find the rational zeros of f of x is equal to x fourth minus x cubed plus x squared minus 3x minus 6. Okay? Well, here's how we do it. We know the rational zeros are going to be on the form P over Q, where P is all the possible factors of the constant term. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all the possible factors of 6. We put plus or minus in there because they could be either. What's your leading coefficient? 1. So your denominator is plus or minus 1. That's all you can do. Well, guess what? What are all those? If you divide by plus or minus 1, you just get the same number. So these could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. That's all the possibilities. Well, that gives you 8 possibilities. Remember, multiplicity could count, and you could have some that are not rational. So where do we go from here? Well, let's just pick the easiest one, 1. Let's see if x equal 1 is a rational zero. It certainly could be, is it? Easy to check 1. Plug in f of 1. And that would be 1 to the 4th minus 1 to the 3rd plus 1 squared minus 3 times 1 minus 6. Now, the reason 1's so easy, all you have to do is add the coefficients. 1 minus 1 plus 1 minus 3 minus 6. Well, if you add those together, what do you get? Minus 10 plus 2 is minus 8. That is not equal to 0. Okay, so 1 is not a rational zero of that function. What's the next easiest one? X equal minus 1. Let's try that one. So f of minus 1 would be minus 1 to the 4th minus 1 cubed plus minus 1 squared minus 3 times minus 1 minus 6. Okay, let's see what that does. Now this one's not quite as easy as plus 1, but it's not too bad. Every even power, when you raise a negative to an even power, is going to be positive. So that's just going to be 1. Minus a minus 1, which is going to be plus 1. Minus a 2 would be a minus 2. Minus a plus would be, minus a minus would be a plus 3, minus 6. Let's add those together and see if we get 0. Minus 6 minus 2, that would be minus 8. plus 3 plus 1 plus 1, that would be plus 4. So that would be minus 4, and that is not equal to 0. 2 down, nothing. Let's try x equal 2. Positive 2. Now, you could plug in positive 2 there, raise 2 to so many powers. In fact, let me go back and show you something else. Let's go back to this x equal minus 1. I'm going to show you a different way. It's actually, minus 1 is easy, okay? So it's not bad to do, but I actually like this method better. This is what I'm going to use from now on. In fact, I'll even use it on 1 when I have to. Do the minus 1 and do synthetic division. Synthetic division, what goes inside is 1, minus 1, 1, minus 3, minus 6. Skip a line, draw a line, bring down the 1. That would be a minus 1, minus 2. That would be a plus 2, 3, minus 3, minus 6. How did I mess this up? Minus 1 does work. Should have done this first. Okay, bring down the 1. Minus 1, minus 2, plus 2, 3, minus 3, minus 6, plus 6, 0. How did I mess that up? That does go in exact number of times. Let's go back and try this again. F of minus 1. See, that's why synthetic division actually works better. That'd be a 1, plus 1, plus 1, plus 3. That's where I messed it up. Minus 6. 3, 4, 5, 6, minus 6. Yeah, I messed that up. Okay, so minus 1 is a 0 because it has 0 remainder. It is a factor, x. Plus 1 is a factor. Okay, so we found one rational 0, minus 1. All right, what do we do next? We try minus 1 again because it could have a multiplicity. So let's do that. Skip a line, draw a line, bring down the 1. That would be minus 1, minus 3, 3, 6, minus 6. Oh, so close. But it doesn't work. It comes up plus 12, not 0. So minus 1 is out. So we'll do this now. Notice another thing I did there, and I wasn't cheating. I wasn't risking anything. You've already determined negative 1 will go in this exact number of times. You don't have to go back to original equation. Just do your next number, negative 1 again, into the quotient. Okay? If it would go into the quotient, it would go into the whole number as well. So if it would have gone into the whole thing, if it was a factor of the quotient, it was a factor of the whole polynomial. So negative 1 didn't work. Let's try 2. 2 times 1 is 2. That gives you 0. 2 times 0 is 0. That gives you 3. 2 times 3 is 6. And look at there. That gives you another 0. So x equal 2 is another 0 of the polynomial. What do you do now? Do you try another? No. Once you get 3 numbers there in your quotient, now you're down to a quadratic. Once you're down to a quadratic, you can either factor or use a quadratic formula. Quadratic represented here is x squared plus 3 is equal to 0. And guess what? You're going to have no real solutions for that. 2 complex solutions, we're not worrying with those. So here your rational zeros, x equal minus 1, x equal positive 2. The others of those are irrational, not irrational, complex. Okay? Now, that's how I did it. Let's see how they did it. Because the leading coefficient is 1, the possible rational zeros are just the factors of the constant term, which are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay? Now, sorry, I'm losing my voice. Okay, those are the possible rational zeros. Start with the simplest one, 1. Okay? And, oh, they just jumped to the 2 that they knew worked. Okay? Shame on them. But the easy thing to do is just add your coefficients, see if 1 works, and then if it does, you still have to do synthetic division with 1. But if it doesn't work, then you don't have to do any synthetic division there. Just go to the next one, like minus 1. And then what you have is a quotient there. Try minus 1 again. Not going to work, so try the next one, 2. This does work, and then after this point, you see no number is going to go into that anymore. Sorry, I'm having trouble breathing. Okay, but when you get down to 3 numbers like this, exclude your 0, okay, 0 remainder, this is a quadratic form, x squared plus 3 equals 0. Has no more real solutions. Certainly no more rational solutions, okay? So the factors then, if you know the rational zeros, x equal minus 1, x equal 2, then you also know the factors, x minus a minus 1, which is x plus 1, and x minus a 2, which is the second factor, and the remaining factor is x squared plus 3. That one can't be factored any further, not in the real number system, and so you're done. So you have found all the possible rational zeros, and in so doing, you also found there's some that you can't express as a rational number. You'd have to form as a complex number. Okay. Because the factor x squared plus 3 produces no real zeros, you can conclude that x equal negative 1, x equal positive 2 are the only real zeros in F, of F, real zeros of F. And that's verified here by this figure. Okay. So there's the graph, sorry. My head's going on me. F of x equal x to the 4th minus x cubed plus x squared minus 3x minus 6. There are your only 2 real zeros. Okay. Even though it looks sort of like a parabola, it's not. It's not symmetric like a parabola is. But it only has the 2 real zeros. The other 2 zeros would be complex. Because it's 4th degree polynomial. It must have it in the complex range. Okay. Part of the problem is this room's getting very cold and that's messing with my head here. I think they skipped one, didn't they? Yeah, example 2 is nowhere on here. Yeah, sorry about that. Let's go back and do example 2. Find the rational zeros of f of x equals x cubed plus x plus 1. Find the rational zeros of that. Well, we know the only possibility would be a p over q, where p is all the possible factors of your constant term, that's just plus or minus 1. Q are all the possible coefficients of your leading term, and that's plus or minus 1. Factors of those coefficients. So basically, this just gives you plus or minus 1. Okay? Now, you can plug in plus 1 and see it's not going to work. That would be 1 plus 1 plus 1. That would be 3. That's not a 0. So don't even mess with that. If you plug in negative 1, I was going to do synthetic division, but I hit the button wrong and it came up backwards. I can't get there. Get my pen back. I'm going to have to pause a minute because my head is sort of clogging up. I'm going to have to run down and get something to, maybe even get a jacket because it's just too cold in here. Sorry about the delay. I had to go get something for my throat. I'm not sure it's any better. It feels better though. So we'll try negative 1 and do synthetic division, and the coefficients are 1, 1, and 1. Okay? If you think about it, it's not going to work either, but let's try it. Bring down the 1, minus 1, 0. That works fine, except this would be 0, 1, not equal to 1. So, oh, sorry. Someone should have caught me on that one. Sorry about that. I messed up synthetic division. How? You have to account for every term. A 0 here, a 1, and a 1. Okay? You have to have one more number than your maximum coefficient, exponent. So you need 4, this exponent 3, you need 4 numbers there. Okay? Bring down the 1, that would be a minus 1, minus 1, 1, 2, minus 2, minus 1. Still doesn't work, okay? So, there aren't any rational zeros for this polynomial, okay? There's one irrational zero, okay? How do I know that? Because there's got to be one real zero. This polynomial is degree 3, okay, which means the end behavior is going in opposite directions. For very large negative x's, that's going to be very large negative. For very large positive x's, that's going to be very large positives. Because it's a polynomial function, it's smooth and continuous. That means it's got to cross the x-axis somewhere, so it's got to have at least one 0. And since those are not rational zeros, they're going to be irrational zeros, 1 or 3. But we won't go there yet. It will be one rational 0, and later we'll see that it's actually going to be a negative rational 0. Okay? So when we did those, if you go back to when we did f of 1 is equal to 3, remember, when you plug in a 1 there, that'd be 1 plus 1 plus 1 is 3. F of negative 1 is minus 1, so there has to be a 0 somewhere between 1 and minus 1. And sure enough, that's close to negative 1. None of the rational zeros work, but it still has to have at least one real 0 between minus 1 and 0. Rational zeros test can't help you find that, but it does let you know that it has to be an irrational number. All right. Then we've already done example 3, and we saw its graph. Okay, and there's its graph. Now, here's where we were. Pick up there. When the leading coefficient of a polynomial is not 1, then the list of possible rational zeros can increase dramatically. In such cases, the search can be shortened in several ways. Number one, if you have a programmable calculator, a graphing calculator, something like that, that can speed up your calculations. It can also show you your graph and give you hints on where to look. The graph drawn either by hand or a graphing utility can give you a good estimate of the location of the zeros. And then the intermediate value theorem, along with a table generated by a graphing utility, can give you approximations of zeros. We've sort of done that type of thing before. Okay? Number four, synthetic division can be used to test the possible rational zeros. That's usually where we begin. So finding the first zero is often the most difficult part. After that, the search is simplified by working with lower degree polynomials obtained after synthetic division, and we did that in example 3. Recall that if x equal a is a 0, then x equal a is a solution for the polynomial equation f of x equals 0. X minus a is a factor of that polynomial f of x. There's lots of things that correspond there. All right, they did that, and they ended it, okay? They didn't do example 4 or 5, and then we'll pick up then in a minute. Let's do 4 and 5. So let's go back. Okay, use this screen and do example 4. Find the rational zeros of f of x is equal to 2x cubed plus 3x squared minus 8x plus 3. Okay, where do we begin? Rational zeros test says that the possible rational zeros will be a form p over q, of course, rational numbers. These have to be integers. And what are the p and q? The p are all the possible factors of the constant term, 3, so that's plus or minus 1, plus or minus 3. Okay? The q are all the possible factorizations of the leading coefficient, which is plus or minus 1 and plus or minus 2. Okay? Now, if you start listing these, you'll see there's more than you might have imagined. Okay? Let's do. I like to start with the whole numbers. That's over 1. So that's plus or minus 1, plus or minus 3. Then use the fractional forms, plus or minus 1 over 2, 1 over 2, and plus or minus 3 over 2, 3 over 2. Okay? Those are all the possible rational zeros. Which is the easiest one to start with? 1. Okay? Now you could do synthetic division, but it's so much easier just to add the coefficients. 1 minus 1 plus 1 minus 3 minus 6. If you add those together, oh, I'm sorry, I'm doing the one we already did. Sorry. Get me out of here, Percy. Okay. Sorry, I did. That's the one we did before. This one. Our coefficients are 2 plus 3 minus 8 plus 3. Well, 3 plus 3 is 6, and 2 is 8, minus 8 is 0. We know x equal 1 is a rational 0. Okay? We know it. We can plug it in and see it. It's so easy to do. Okay? But, since it is 1, you still have to do synthetic division. So do it. 1 on the outside, then put your coefficients 2, 3, minus 8, and 3. Always check the maximum exponent is 3. You have 4 numbers. That's what you need. Bring down to 2. 1 times 2 is 2. 2 and 3 is 5. 1 times 5 is 5. Negative 8 plus 5 is negative 3. 1 times negative 3 is negative 3. Plus 3 is 0. We knew that. We knew it was going to come out 0 because when we plugged it in, we got a 0. However, we now know what's left over. The quotient is this. 2x squared plus 5x minus 3. Okay? We set that equal to 0 and see if we can factor it. Now, there's no guarantee that we can, but let's see if we can. Only possible factorization for 2x squared would be 2x times x. Now, only possible factorizations of 3 would be, negative 3 specifically, would be minus 3 and 1, or 1 and minus 3, or minus 1 and 3. I mean, there's any combination of those. Let's just try plus 3 minus 1. Okay? Don't know if that's going to work. Let's see. 2x times x is 2x squared. That works. Minus 2x plus 3x would be plus x. That doesn't work. So therefore, let's change the numbers. My number's wrong, so let's change the number. Put the 1 here and the 3 there. Okay? Put the 1 here, 3 there. Okay, let's see if that works. 2x times x is 2x squared. Minus 6x plus x would be minus 5x. Ha! The number's right, but the sign's wrong, so I'll take off the plus there and put on a plus here. Now let's try it again. 2x times x is 2x squared. That's fine. Plus 6x minus x is plus 5x minus 3. That works. So what are our other two zeros? Well, 2x minus 1 equals 0. Solve for x, and you get, add 1 to both sides. You get 2x is equal to 1. Divide by 2, and you get x equal 1/2. And sure enough, this was one of our possibilities, x equal 1/2. Okay? And what's our other one? X plus 3 equals 0. Well, that add or subtract 3 from both sides, you get x equal negative 3. And sure enough, that was one of our possibilities too. So we found our 3 zeros. You only needed 1 for synthetic division to get it down to a quadratic. Then we factored that and saw what the other two were. So it said our problem was find the rational zeros. X equal 1, x equal 1/2, and x equal negative 3. All 3 rational zeros. Don't look for any more, because the maximum you can ever have is 3. You got them, all 3 of them. Now, let's just take it one more step. What's the factorization of this thing? They didn't ask for it, but we can now do it. That would be x minus 1 times x minus 1/2 times x plus 3. Not quite, though. Those are the factors, but notice that x times x times x would be x cubed, not 2x cubed. You need a 2 out in front to make it a 2x cubed. Okay? And by doing that, you could have changed this factor to be multiplied to 2 by that, and you could have had x minus 1 times 2x minus 1 times x plus 3. And the 2x minus 1, yeah, we saw that was a factor there too. So we got the factorization. X equal 1 is a 0, so x minus 1 is a factor. Then the other two factors are 2x minus 1 and x plus 3. So this then is the complete factorization of that. Okay? I hope that makes sense. Again, and by the way, that's what the book has too. Let's see. It says find the rational zeros, so it's x equal 1, x equal 1/2, and x equal negative 3. And we also found the complete factorization, which is x minus 1 times 2x minus 1 times x plus 3. There is a checkpoint, and since you're not in class to do these, I'd suggest do these checkpoints. All right, let's do example 5. They didn't draw a graph there. And they just say you can't factor cubes very easily. I mean, you could try factoring by grouping. That's not going to work on this one. You know, sometimes it might, but they're fairly rare that it does. So you just have to go through this procedure. Rational zeros test, big help. Okay? So let's do example 5. Okay? Find all the real solutions for this one. Negative 10x cubed plus 15x squared plus 16x minus 12 equals 0. It says find all the real solutions for that polynomial equation. Okay? Not writing it as a polynomial function, but it is. I mean, you're finding the zeros, so it's the same thing. Real solutions, that's the same as the zeros. So where would you begin? Well, first thing I would do is look and make sure we don't have any common factors. This is 2 times 5, this is 3 times 5, this is 2 times 2 times 2 times 2. No common factors. But when I go to do my rational zeros, I see that's P over Q, where P over Q, all the possible factors of 12 and all the possible factors of 10. Okay? Well, when you do those, remember we eliminate any that are, how did they say it at the beginning? Where P and Q have no common factors other than 1. Well, the common factors here are obviously 2. So don't include that. So if you eliminate that, that would be 5 and 6. So this will be common is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are all the possible factors of 6. Your denominator, plus or minus 1, plus or minus 5. Because you took out the common factor 2 between 10 and 12. Okay? Now, let's list them. Again, I kind of like to list the whole numbers first, or integers first, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Then that's each of these over 1. Then do each over 5. That would be plus or minus 1/5, plus or minus 2/5, plus or minus 3/5, and plus or minus 6/5. Those are all the possible factorizations. My word, that's 2, 4, 6, 8, 10, 12, 14, 16. You can only have 3, so certainly not all of these are going to work. But what's the easiest one to try? Plus 1. Plus 1 is so easy to do, you just add the coefficients. Minus 10, plus 15, minus 16, minus 12. Let's add those together. Add the, oops, that's a plus there. Add the minuses together, you get minus 22. Add the pluses together, and you get plus 31. So obviously 1 doesn't work. Don't even bother synthetic division with 1. But we can do synthetic division with minus 1. Okay, and when you do synthetic division here, we put minus 10, 15, 16, minus 12. Okay, you have 4 numbers, maximum exponent's 3, that works. Skip a line, draw a line, bring down the minus 10. Then do your synthetic division. That would be at 10, 25, negative 25. Add that and you get negative 9, 9, and negative 3. Obviously, that's not 0, so that won't work. So minus 1 is not a rational 0. So we'll not use minus 1, and we'll start over with everything else being the same. Okay? Well, what's the next one? I like 2, so let's try 2. That would be minus 20. That will be a minus 5. That'll be a minus 10. That'll be a 6. That will be a 12. And that's a 0. Ding, 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 ding. We've got a winner. X equal to is a 0. That's a solution to that polynomial equation. X equal to is a solution. Is that the only solution? Let's see. What we have left is minus 10 x squared minus 5x plus 6 equals 0. Now, We could try factoring that. Trial and error, you could run into a lot of trials and a lot of errors. So you might also try the AC method. Okay, let's try that one. AC, in this case, is minus 60. So we want two numbers that multiply to be minus 60, but add to be minus 5. So the B is equal to negative 5. So two numbers, obviously, that multiply to be negative 60, one's got to be plus and one's got to be minus to get a minus answer. The larger number better be the minus one, because you got B, which is, call this m times n, and this is m plus n. So the larger number, numerical value, needs to be the negative. All right, so let's do that. 1 times negative 60, well, those add to be negative 59, not negative 5. That won't work. 2, negative 30, that adds to be negative 28, not negative 5. 3 times negative 20, that adds to be minus 17, not negative 5. Okay, let me go on up here. 4 times minus 15, that adds to be minus 11, not minus 5. 5 times minus 12, that adds to be minus 7, not minus 5. If we're going to hit it, we better hit it soon. 6 times negative 10, and that would give you negative 60, but when you add those, you get negative 4. That doesn't either. You've already passed negative 5. You see, you were bracketing it. You already went past it. That means there's no more whole numbers that are going to work. Okay? No factorization is going to work. That means the other two are going to be either irrational or complex. Well, how can you tell which they are? Well, you can use the quadratic formula. Factoring didn't work, or at least we didn't get it to work. I hope I didn't do anything stupid there. But let's see if we can, what your quadratic formula tells you. Quadratic formula says x is minus b, which is 5, plus or minus the square root of negative 5 squared would be 25, minus 4 times a, which is minus 10, times c, which is 6, and I see, and that's all over 2a, which is 2 times negative 10. Okay, so this is going to be 5 plus or minus the square root of 25, and then if you multiply them together, count your negative signs. 2, that means that's going to be a plus. That's good. It means it's not going to be complex numbers. They'll be irrational, hopefully. Okay. Well, 4 times 6 is 24, so that's 240. Okay, over a negative 20. Okay, this will be 5 plus or minus the square root of 225. No, 265. I can't read my writing. 265, and that's over negative 20. And I think with a little bit of work there, you'll see 265 is not a perfect square. Okay. I don't have a calculator in here to tell you, but I think these come out to be irrational numbers. So the other conjugate pair of irrational numbers, those are the other two zeros. But all it asks for the rational zeros, you only have one. Okay? No, I'm sorry. It says find all real solutions. So therefore, we do need to do our rational zeros. And like we said, I got minus 5. Oh, man. Okay. No. Oh, okay, I see what they did. I did the b's just like they gave them to us. And you got this. What the book did was multiply numerator and denominator by -1, and they came up with -5 minus or plus, it doesn't matter which order, the square root of 265 over 20. Same answer, I mean same result, but you'll see those are irrational numbers. Square root of 265 is not rational, so just plug it in and see what you get. One of these, and you can do either one you want to. I like the way I did it better. 5 plus the square root of 265 over a -20, or 5 minus the square root of 265 over a -20. Those are your two possible solutions. They are -1.0639 approximately and -0.5639. Okay, so you've got your three possible solutions. One is a rational number. That was 2, x equal 2. And you see that on the graph. Yeah, they don't show the graph either. And then the other two are irrational numbers. Okay, another checkpoint. I would certainly pay attention to that. All right, that finishes those examples. Now, the next part talks about conjugate pairs. This is talking about, and I just mentioned them by the way, irrational numbers typically show up as conjugate pairs, and complex numbers show up as complex conjugate pairs. Now, I think they're going to be talking here mostly about complex conjugate pairs, which we just sort of skimmed over before, and we're going to continue skimming over it. But I will point out the big picture for you, but you're not responsible for the complex numbers. It's not in the course description. If you need it in your major, you'll run into it and find it. We've talked enough about it, but let's just hit the high points here. Again, I'll try not to test you on this. Note that the pair of complex numbers, complex zeros, are conjugates of each other. That is, they are of the form a plus bi and a minus bi. Okay, now that was in say example 3. Would have done that if you had carried it that far. Example 2 would have had that if you had carried it that far. Okay, so they just said note this. Let me say when this is true. This is true when you have integral coefficients. Then your complex zeros are conjugate of each other. If you have complex coefficients, all bets are off. They don't have to be conjugate pairs anymore. But again, you're not responsible for this. So here's the, what do they call this? Just a notation here. Let f be a polynomial function that has real coefficients. Like I was saying, real coefficients. I said integral. For this to be true, all it needs is if a plus bi, where b is not equal to 0, in other words, this has an imaginary part to it, is a 0 of the function, then you know that a minus bi also is a 0 of the function. That's anytime you have real coefficients. If you have complex coefficients, yeah, not true. But real coefficients it does. Be sure you see that this result is true only when the polynomial has real coefficients. That means they could be irrational numbers, they could be fractions, decimals, they just got to be real. For instance, the result applies to the function f of x equal x squared plus 1, but not to the function g of x is equal to x minus I, because I is not a real number. Okay, so you just have to have, not just, you have to have real coefficients, real numbers. They don't have to be integers like that x squared plus 1 is, but it could be x squared plus 0.5, or x squared plus the square root of 2, They could be any kind of numbers like that, rational, irrational, they just have to be real. But if they have a complex coefficient, yeah, then that doesn't work. So find a fourth degree polynomial function with real coefficients that has x minus 1, minus 1, and 3i as zeros. It says a fourth degree polynomial function with real coefficients. Well, since it has real coefficients, that means any complex zero its conjugate will be. Well, there's a complex zero. Its conjugate is minus 3i. Well, how many zeros we got now? 1, 2, 3, 4. So therefore, we've got them all. Fourth degree polynomial, 4 zeros. So what is that fourth degree polynomial with real coefficients that has those zeros? Well, we know that f of x would be, I can't write it in any old form, but I can write it in factored form. X plus 1, that's from that 0, times x plus 1 again, that's from that 0, times x minus 3i, that's from that 0, times x plus 3i, and that's from that 0. Okay? Now I can multiply those together and see what we get. And again, you're not responsible for this, though you may have this to do without the complex zero. You may have real zeros and still have to be asked a question like this, so that's why I wanted to show it to you. But multiply those two together, that's x squared plus 2x plus 1. Multiply those two together, complex conjugates of each other, that gives you x squared plus 9. Okay? If you don't believe me, fool it. X times x is x squared plus 3ix minus 3ix, that adds a 0, and plus 3i times minus 3i, that would be minus 9 times I squared, but I squared is minus 1, so that would be plus 9. Then we can, it's not exactly a falling, but it's like it, multiply first, each of these that way. That would be x to the fourth. Now I'm going to cheat a little bit because I like to put them in the right order. Then we're going to have plus 2x cubed, and that's the only x cubed term you've got. And then we've got plus 9x squared, that's from those two. But then you have a plus x squared, that's from those two. And then we have a plus 18x, that's from those two. And then we have a plus 1. Okay? That should be 6 terms that we have, because you got 3 times 2 is 6. 1, 2, 3, 4, 5, 6. Yeah, we got them combined like terms. X to the fourth plus 2x cubed plus 10x squared plus 18x plus 1. Okay? Now, is that the only one? No. You can multiply this by any number in the world, a sub n. Any number you wanted to. And you still have one that factors like this. Okay? So that's how you find a fourth degree polynomial. Let's see what they got and how they got it. They first determined, minus 3i has to be a 0. Then they did the linear factorization. I did a sub n. They just said a. And when you, they said a equal 1, which is going to be giving us exactly what we got. The x plus 1 times x plus 1 is x squared plus 2x plus 1. The x minus 3i times x plus 3i is x squared plus 9, like we said. And so we get x squared plus 2x plus 1 times x squared plus 9. Multiply those out, you get x fourth plus 2x cubed plus 10x squared plus 18x plus 9. There's your answer. Now, because of the 3i, you won't have any like that on it, but you could have all real factors like that, and you could still find that polynomial. Okay. That was example 6. We've done it. Now let's deal with factoring a polynomial. which is what we've been doing, so to speak. So let's see what we got. Linear factorization theorem shows that you can write any nth degree polynomial as a product of n linear factors. Remember that? F of x is equal to some coefficient, and now they're saying a sub n, x minus c1 times x minus c2 times x minus c3, all the way up to x minus c to the n, okay, sub n. However, this result includes the possibility of some of the factors ci are complex. Some may be multiplicities, okay? Some may be irrational, okay? But they're just any complex numbers, okay? The following theorem says that even if you do not want to get involved with the complex factors, you can still write f of x as a product of linear and or quadratic factors. Because if they are complex, they always multiply to be a quadratic, okay? So the factors of a polynomial, every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. Okay? That's what we're going to be responsible for. So those quadratic factors with no real zeros are said to be prime or irreducible over the real number system. Note that is not the same as being irreducible over rationals, okay? That would be if they factor, okay? This is irreducible over the reals. For example, the quadratic x squared plus 1 cannot be factored over the real number system. It can with complex numbers, but not with reals, okay? And therefore, rationals either. Okay. On the other hand, the quadratic square root x squared minus 2, well, that is kind of a difference of two perfect squares. X times x is x squared. Square root of 2 times square root of 2 is 2, so that would be x plus square root of 2 times x minus square root of 2. That would be non-reducible over rational numbers, but it is reducible over reals. Okay? So that's what we're dealing with here. So let's see, yeah, the next example, and do we have time for it? I can't read my, yeah, I think we have 3 minutes. Let's try it. Find all the zeros of f of x equal x to the fourth minus 3x squared plus 3x cubed plus 6x squared plus 2x minus 60. And then they say, given that 1 plus 3i is a 0, okay? Well, if you know that's a 0, then you also know that 1 minus 3i is a 0 because all these coefficients are real numbers, okay? So if that's also a 0, then multiply those two together and you get 1 plus 9. Well, I'm sorry, x minus that times x plus, x minus this, sorry. Yuck. Well, I can't get the eraser to come up. Okay. All right. Okay. X minus that times x minus that, those would be your factors, and when you multiply those together, it would be x squared plus, and when you square this, that's what I was doing a minute ago, it's x squared minus this thing squared. Well, this thing squared would be minus the square of that. When you multiply these two together, you get 10. Okay? 1 squared minus 9 times I squared, which is plus 9. So x squared plus 10. That's going to be the factor for those. Okay? Now, if that's a factor, then you could do rational zeros test, or you could do long division, right? If that's a factor, then it'll go into that. You can't do synthetic division, so do long division. X squared plus 0x plus 10 into x to the fourth minus 3x cubed plus 6x squared. I think we're out of time. I think we're going to have to pick up next time. Sorry about this. We'll pick up next time with example 7. I'm only doing it because, except for the complex part of that, we still can do it, okay? And we will pick up and go from there, okay? So we'll pick up with example 7. Homework exercises here. Whoa, this is a long section. You can do any of the odds, 9 through 13, any of the odds, either 15 or 17, or both, any of the odds 19 through 27, either 29 or 31, or both, either 33 or 35, or both, either 33 or 37 or 39, or both. And then you can try 41 or 43. They may get a little wacko there. I mean, it says use a graphing utility. If you don't have one, don't mess with it. But do what you can on those. Just take a look at them. And then you can play around with 45 to 49, but those all have imaginary components, so you don't have to do those unless you just want to mess with them. I think you could do either 51 or 53. Actually, stop, because we'll do, when we do the one we're working on now, example 7, then we'll come back and do 51 or 53. So stop at 49. Good deal. That covers everything we need to today, and we'll pick up and go on Thursday morning.